Let's consider color blindness in the US. And the kind of color blindness we're referencing here is red-green color blindness. So people can't distinguish red and green in general. And I've had several students that had this, and it was always a problem if I was writing in red on a white background, that hardly showed up for them. So I've had classes before where I had students say, hey, you can't write in red, I can't see it. So in the US, 7% of men are colorblind. So just thinking about what that means in some other language, like, again, I keep mentioning English is kind of difficult sometimes. Other ways I could state that, the chance of being colorblind if one is male is 0.07. So I can state that as a decimal. And so depending on the situation, sometimes we'll state things as a decimal, sometimes as a percent, sometimes as a fraction, and they each have their own benefits there. Let's look at women. 0.4% of women in the US are colorblind. Another way I could state that, so I could use that same language in there, but I just want to kind of play around with getting used to language versus probability. The proportion of women in the US that are colorblind is, as a decimal, would be 0.004. So let's think about that for a minute. Oops, I forgot my percent there. So 0.4%, 0.4 would be the proper way to read that. So it's less than a whole percent. A whole percent, 1% would be 1%, means out of 100, so 100th would be right here. So this has to be 0.4 of 100 or 4,000ths. So 4 in 1,000 women in the US are red, green colorblind. 7 out of 100 men, right? So that's what this one means, 7 in 100, 7 out of 100, versus this one right here, we can consider 4 out of 1,000. So 4 in every 1,000 women, 4,000ths are colorblind. With the women, let's keep talking about that. We could restate it with the if or put it in the notation. So the chance to do both a woman is colorblind is 0.4%, 0.4%. Let's see what else can we say. The chance person is colorblind is 0.4% if they're a woman. And again, I keep mentioning human language is a problem. It's very varied. There's lots of ways to say something, and sometimes the way we say things isn't quite precise. In statistics, we try to summarize that just to be clear. So the probability of being colorblind, let's call that CB, if they're a woman, that's that 0.004, 0.004%. All right, so let's look at some variations on this. Some other questions we can ask. So we know that the probability of being colorblind, if we have a male, is 7%. We know the probability of being colorblind, if they're female, is 0.4%. So what would be the probability that a randomly selected female is not colorblind? Now, some things to think about here. We're only selecting females, so that's the only thing in our population, and we want to know if they're not colorblind. So that would be the probability that they're not colorblind if they're a woman. And several ways to think about that. The easiest one is, well, that's just the opposite of this probability. So that would be 1 minus the probability they're colorblind if they're female. So that would be 1 minus 0.004. Now, if I put the 1 there, I have to use a decimal. If I want to stick with the percent, then I would have to write 100% minus 0.4%. And either one should give me the same answer. So let's look on a calculator, think about that. Cards for now. First thought was 1 minus 0.004, which gives me 0.996. We change that to a percentage, we would shift the decimal point over twice, so that would be the same as 99.6%. And if you think about this right here, we're taking away less than 1% from 100, so we should still have 99 plus a little, and that 0.6 plus 0.4 gives us that missing 1%. So either way, we're going to get the same answer there, depending on how it needs to be stated as a decimal or as a percentage. All right, let's try another. How about the probability that a randomly selected male and female are both not colorblind. So we already know about the probability of having a woman that's not colorblind. The probability of a man is pretty similar. So probability of not being colorblind if they're male, right? Because we're only looking at males at first. That would be 1 minus that 7% or 100% minus 7%. 93%, or 0.93, 93 hundredths. Now here, we're looking at and both. So that one right there is related to that multiplication rule. So now I want to know what's the probability that we have a not colorblind male and we have a not colorblind if female. And implies a multiplication of the two. And then we have that extra catch that what's the probability of having a female that's not colorblind if we know the male is not colorblind? Now, we're going under the assumption that half the population is male and half is female, and so that we already selected a male has really nothing to do that we're now selecting a female. So being a male is independent of being a female most of the time. So this would be the probability of the not colorblind males times the probability of not colorblind if female. And so that would give me the male probability, so 93% of them are not colorblind. And what do we have for females? 99.6. So let's see what we get there. Got the 99.6 times the 93%. And we're going to get roughly 92.6% if we go to 3 decimal places. So that's approximately 92.6%. And again, technically we have to consider this formula back here. So the probability of having a colorblind male if we already have a colorblind female. So females aren't males, so that means they're independent under that assumption. All right, what about probability that at least one of the two being the male and the female, is colorblind. All right, so this one's a little trickier because I've got the at least going on, at least one. So let's see, if I could have at least 1 cup of coffee, I could have 1 or 2 or 3. And we only have 2 people here. So the options for at least one being colorblind. So if we think about colorblind out of 2 people, either we could have none of them are colorblind, I could have one of them is colorblind, or both of them could be colorblind, right? So either 0, 1, or 2. This question here is saying at least one, so they're saying, all right, is one of them colorblind or 2 of them colorblind? Okay, so let's think about that for a minute. Well, if one of them is colorblind, that means I want the probability of having a colorblind male, or I could have a colorblind female. Both of them, that would be the probability of, oops, and I put my parentheses in the wrong spot. We'll fix that in a second. Colorblind male and colorblind female. And this one right here, I kind of jumped ahead a little bit. Technically, I should have written that that's the probability of a colorblind if male, and the or colorblind if female. And our rule about the or would be consider them separately and add them up, but then from that, you should subtract the probability that they're both colorblind. Get that right? No.
I was going to say, when you subtract the
statistics,
if they're neither of them are colorblind.
Yeah, so it turns out actually this isn't what I wanted to think about here. As far as counting if one of them is colorblind, either it's a female that's colorblind or it's a male. So I just need this number on its own and that number on its own. I'm not thinking about them both happening at the same time. For the at least one, it could be one male, it could be one female, or it could be both. So those are the different options there. So for this first one right here, that would be 7%, so 0.07. For the second one right here, that's just, I find a colorblind female, so that would be 0.004, 0.4%, and the and would just be the multiplication of the two of them. So that would be and 0.07 times 0.004. And let's see, the 92.6%, that would be the probability that they're both not colorblind. Now, that's an interesting idea here. So let's go back for a second. I'm glad you brought that up. This one right here is the probability that they're both not colorblind. Right? Which is the opposite of what I'm trying to calculate here. And remember, we have that rule about complementary events, that the probability of not A happening is equal to 1 minus the probability that A does happen, or vice versa. The probability that A happens is always 1 minus the probability that A does not happen. So here, this right here, I'm kind of considering, well, here's what I think the probability A is, where A is 1 or 2 people are colorblind. And so let me just calculate that, and then I'll think about it the other way that Bree mentioned. So I want to know what is 0.07 plus 0.004 plus the multiplication of those two. And again, I could just click here, but I find it easier to type up there than click on this pad. All right, so did I type that right? 0.07, 004, and then there's the multiplication. Yeah, so I get about, if I go to 3 decimal places, 7.4%. So 0.074 if I go with that, rounding to 3 decimal places. So this is about 0.074 or 7.4% chance of finding at least 1 out of 2 male and a female that are colorblind. Now, if I think about it the other way, we calculated this probability that neither are colorblind on the other page. So that probability was 0.926. And if I take 1 minus 0.926, we should get the 7.4%. So clear 1 minus 0.926. So there's that 7.4. So often with probabilities, there's multiple ways to get at the answer. Usually I just want to find one, but sometimes I look at it a different way to see if I'm on the right track, because it's so easy to ask a question about probability that seems easy at first glance, but it's actually a really hard problem. And pretty much anytime somebody asks me a new probability question, I got to think about it really hard, write down a bunch of different things about it, and do it a couple different ways before I can come up with an answer. So these are tough problems. All right, so I just want to go over another way to answer questions like this. And I started doing this the other day, and that is by making a table of values related to those probabilities. So I'll start setting it up on my paper, and then I'm going to jump into a spreadsheet, and I'll share that spreadsheet with you.